Hello and welcome to this lesson about continuous functions. My name is Mohamed Kadem Kare. You may download the PDF of this lesson on the website I indicate here. The outline of the presentation will be firstly to define continuity, then to give its basic properties. After that, I will state the intermediate value theorem, and finally I will show you the continuous extension. We begin by defining continuity. So the intuition behind this notion is as follows. A function is said to be continuous if we can draw its curve without lifting the pencil. Here's an example. So this function here is continuous since I can draw its curve without lifting my pencil. The second example here is not continuous at this point since I was obliged to lift my pencil to draw its curve. We say that a function is continuous at a if the limit of the function at point A equals f of a. So this is the mathematical definition and the formal definition of continuity which formalize this intuition here. The limit of the function at the point A should be equal to the value of the function at this point. We say that a function is continuous on a set I if f is continuous at any point A in I. Let's now give an example. Here is a function defined by this expression when x is smaller than 2, and this other expression here, x plus 1, when x is strictly larger than 2. So in order to calculate the limit of this function on the left of point 2, we use this expression here. Because on the left, I make a figure to make things more clear. Here is the point 2. So on the left of point 2, we have the expression which is this one, 2 multiplied by x minus 1. So to calculate the limit on the left of 2, we use this expression here, 2 multiplied by 2 minus 1, which gives the value 3. On the right side of 2, we use this second expression, and we get 2 plus 1, which gives also the value 3. So we have here another curve, but it gives the same value, 3, also on the right side of 2. Then, consequently, the limit of this function at point 2 exists, and it is equal to the value 3. So in the particular case, if we define the value f of 2 to be equal to the limit 3, in this case, the function will be continuous at point 2. So for continuity to hold, we should define the value of the function at this point as being equal to the limit at this point, which is 3. A useful theorem says that all polynomial functions, such as x, x squared, or any combination of powers of x, are indeed continuous functions. Let's present the basic properties of continuity. A first theorem says that if we take two functions f and g to be continuous, then their sum, f plus g, is also continuous. Also, the product, f multiplied by g, is continuous. The ratio, f divided by g, is continuous at any point A where g is non-zero. The second theorem says that the composition of two continuous functions is continuous. More precisely, if f is continuous at a and g is continuous at f of a, then the composition g composed with f is continuous at point A. Here is an example. If we take the function f as x to the power 3 plus 4, which is continuous, and the function square root, which is also continuous, then the composition, which is the square root of x to the power 3 plus 4, is also continuous. We state now the intermediate value theorem, which permits to show that an equation admits a solution without solving explicitly this equation. Here is the statement of this very useful theorem. Let f be a function from an interval ab to the set of real numbers, assumed continuous. Then for any value k between f of a and f of b, there exists at least one c in the interval ab such that f of c equals k. Here is a figure to illustrate this idea. So consider that, for example, f of a is here. So this is a, this is b, and this is the value of the function f at point A, and this is the value of the function f at point B. So this is the first point, this is the second one. And if you take any value k between these two values f of a and f of b, necessarily there is some c here such that f of c equals k. And this is due to the fact that the function is continuous, so it passes through all the points between f of a and f of b. Okay? If, moreover, the function is strictly monotone between these two values, here an example of a function strictly increasing between f of a and f of b, if f is strictly monotone, increasing or decreasing, then c is unique in this case. And as a consequence of this theorem, we have this corollary, which says that if f is a continuous function on an interval ab, such that f of a and f of b have opposite signs, then there is at least one c such that f of c equals 0. In other words, if this product here is strictly negative and f is a continuous function on the interval ab, then there exists some c such that f of c equals 0. So let's make a figure to illustrate this corollary. Here we have a, and this is the value of the function at point A. This is b, and this is the value of the function at point B. I consider the case where the function is negative at point A and positive at point B. So we have to start from this point and go to this one. Since the function is continuous, then there is some c where the function equals 0. If, moreover, f is strictly monotone, then c is unique. Okay? So here in my example, the function is strictly increasing, so the c is unique. Of course, if the function is not monotone, then there is no necessity for c to be unique. Okay? Here, for example, there are 3 possible values of c where the function equals 0. The last remark in this slide is that the interval ab may be open, like that, or sometimes semi-open. For example, it is open at E and closed at B. In this case, we should replace f of E, or the value of f at B, by the limits. For example, the value of f at point A should be replaced by the limit of f when x goes to A, or the limit of f at point B. Moreover, A and B, when the interval is open, may be infinite. And in this case, of course, there is no value of the function at infinity, so we should consider the limits in place of the value of the function at these points. So here, a graph of a function to illustrate the intermediate value theorem. So the function has this expression. You see that at point 1 the function is negative, whereas at point 2 the function is positive. So there is some c here where the function equals 0. And mathematically we can treat this example by calculating the value of the function at point 1, and this gives the value -1. The value of the function at point 2 equals 4. So these two values have different signs, so there is at least one c such that the function equals 0. Moreover, if we calculate the derivative of this function, it gives this function here. From the expression of f you can get its derivative. The discriminant of this polynomial equals -8, which is negative, so the derivative will be positive at any point x. And consequently, the function is strictly increasing, so the value c, where the function vanishes, is unique. So you see that we can't solve explicitly the equation, this equation equals 0. Nevertheless, we can prove that there is some c such that the equation have a solution, so there is some c such that f of c equals 0, and moreover we can prove that this value c is unique. So this is the importance of the intermediate value theorem. The last part of this lesson concerns continuous extension. So let f be a function which is continuous from R minus a singleton A, such that the limit of the function at point A exists and it is a real number denoted L. In this case, we define a new function g by letting g equal to f if x is different from A, and we define g to be equal to the limit L if x equals A. This function is called continuous extension of f at point A. So this is the definition of continuous extension. Here is an example. Consider the function defined by this expression for n x different from 0. So you see that the function is not defined at 0 since the denominator equals 0 when x equals 0. Nevertheless, the limit of the function when x goes to 0 equals 2. You can see this by multiplying the denominator with the conjugate form, square root of x squared plus 1 plus 1, and multiplying both sides by the conjugate form, you see that x squared may be simplified, and when now x in the remaining term we replace x by 0, we get the value 2. So the continuous extension of this function is defined to be equal to the expression of f when x is different from 0, and precisely for the point x equals 0, we take g to be equal to the value 2, which is the limit. Okay, this is the continuous extension of the function f. Okay, I hope that this lesson was clear and useful for you. Have a good day and see you in the next lesson. Goodbye.